The fluidized bed reactor is the heart of UNIPOL's low-pressure gas phase process for the manufacture of polyethylene and polypropylene. The fluidizing medium, cycle gas, is composed of the monomer and comonomers, hydrogen, nitrogen, and other inerts. The cycle gas removes the heat of polymerization from the growing resin particles and agitates the solid particles to provide good mixing and heat transfer to prevent agglomeration of resin. Fluidization is a phenomena in which a bed of solid particles is transformed into a fluid-like state by an upward-flowing liquid or gas. The UNIPOL gas phase process utilizes either gas or gas with some liquid as the fluidizing medium. When a gas flows upward through a bed of solid particles at a low velocity, the gas moves through the voids between the solid particles and the solid particles remains as a stationary packed bed. As the gas velocity increases, the particles in the bed begin to move. The bed starts to expand, and the pressure drop across the bed increases until the pressure drop through the bed equals the weight of the bed. The gas velocity will increase the pressure drop until the bed is fluidized. Once the bed is fluidized, further increases in the gas velocity will not increase this pressure drop. The minimum gas velocity at which the pressure drop equals the bed weight is called the minimum fluidization velocity. At minimum fluidization, the particles in the fixed bed begin to move or hover. As the gas velocity increases, the bed expands and bubbles begin to form which promote radial and axial mixing of the solid particles in the bed. If the gas flow becomes excessive, the bubbling bed starts to slug. The bed will become more turbulent and start to segregate, thus causing carryover of the resin bed throughout the cycle system. The UNIPOL fluidized bed behaves like a liquid of the same density. Some characteristics of a fluid bed are: the fluidized particles flow easily through openings in the sides of a vessel. The pressure drop between 2 points in the bed can be used to infer bed weight, bed height, and fluidized bulk density similar to a tank full of liquid. The pressure drop across the bed is constant and does not increase with increasing gas velocity once minimum fluidization is reached. The solid particles are in continuous movement, which result in rapid and good mixing of solids. A uniform temperature profile exists across the bed due to the good solids mixing. Excellent heat transfer exists between the fluidized bed and the walls of the container or any surface immersed in the fluidized bed. There are two aspects to consider when discussing fluidization: the bubbles and the gas and solid flows. These will be discussed separately. There are two types of gas flow in a fluidized bed. Most of the gas flows through the voids between the resin particles providing fluidization. The rest of the gas flows upward in the form of bubbles and causes the mixing. In a fluidized bed of granular resin, the bubbles are constantly changing in size. Relatively small bubbles form at the holes in the distribution plate. These bubbles coalesce or combine as they rise to form large bubbles at the top of the bed. Occasionally, large bubbles break up to form smaller ones. The size of the bubbles present at a given bed height will increase with increasing gas velocity. The most important feature of bubbles in the UNIPOL gas phase process is that movement of bubbles result in the mixing of the solid particles. This is because solids are drawn up behind a bubble and form a wake. As the bubble size increases, the size of the wake increases, and therefore the amount of solids which are drawn up through the bed behind the bubble also increases. Good solids mixing is necessary for rapid distribution of catalyst and for efficient heat transfer that prevents the agglomeration of resin and produces a uniform product. Since bubbles are the primary driving force for the movement of solids, the solids mixing rate is usually assumed to be proportional to the volume of bubbles. Quantity of bubbles increases with cycle gas velocity. This emphasizes the importance of velocity. The gas flows through the distributor plate holes to form small bubbles across the entire cross-section. As the bubbles rise in the bed, they combine to become larger bubbles. The larger bubbles tend to move toward the center of the bed. However, some small bubbles still rise near the reactor walls, with less frequency than at the center. The pattern of bubble flow in the fluidized bed result in a solid circulation pattern of two cells. At the lower level of the bed, a small circulation loop develops in which the solids tend to move upward near the reactor walls and downward in the center. At the middle and upper levels of the bed, a big circulation loop develops where solids tend to move upward in the center of the bed and downward near the walls. The point where the two circulation cells meet is called the null zone. The null zone can move slightly up or down the bed height by decreasing or increasing the superficial gas velocity. At high superficial gas velocities, the small lower circulation cell disappears, leaving a single large circulation cell. One of the most important functions of the fluidized bed reactor is to evenly disperse the catalyst throughout the bed. Poor catalyst dispersion will result in hot spots that can cause resin agglomeration, forming chunks or sheets. The optimum location point for catalyst injection is near the bottom of the fluidized bed, away from the reactor wall.